So the next technique I'm going to go into is multiple instance learning. And this is something that, these slides are actually ones that I've used in my very own work. And it's something that I've looked into myself, and we'll get into that a little bit later on. So first of all, let's define multiple instance learning. And I'm going to use a definition that was proposed in 1997, and the paper is given at the bottom here. And the idea of multiple instance learning, according to this paper here, was that instead of labeling each individual instance, so here I've labeled cancer patches and healthy patches, instead of doing it like so, we can group them all together and place them into a bag, and instead label that bag instead. So here I've labeled that bag as cancer. Now, this was originally proposed for a binary classification problem, so that it was positive and negative instances. So here, positive instance refers to cancer, negative instance refers to healthy. And there were two conditions attached to that binary problem. So one was that if a bag was labeled as positive, in other words, if I label a bag as cancerous, only at least one instance within that bag had to contain cancer, and the rest could be healthy. However, if I labeled a bag as negative or healthy, then all of the instances within that bag had to be healthy. And by doing that, you're constraining your problem to give your model something that's absolutely certain what is healthy, and only unsure about one particular class in this particular setup. So it only has to figure out what instances are most similar to the negative bags, in which case are incorrectly placed into the positive bags. And the way it was done, in 1997 and then further on, was usually using bag of word features or distance-based metrics such as Euclidean distance. There were a lot of other techniques, but they all tended to be distance-based metrics or clustering measures, or some way of kind of downsampling the original instances into a small feature encoding, and then using that encoding in order to pull apart negative and positive instances. So obviously in a deep learning framework, we need to reformulate this in a different way. So there's a lot of techniques which use this. So obviously I've showed you some in the medical domain, but you may also use this in real world data sets, because here, for example, the sky has a bounding box around it, but it doesn't completely surround the sky, and you've got some of the beach in the beach class as well. So there's a lot of overlap in this particular example. And in zero shot and few shot learning, you've come across very similar problem setups as well, where it's just not feasible to label absolutely everything. Another really interesting example, in fact, I would say it's more commonly used in text data than it is in image data. And so I made up this example very quickly. I took a paragraph from Alice in Wonderland and just put it in here. And the task here is to classify whether this came from a sci-fi, fantasy, or romance book. So here I bolded out certain pieces of text. So if we put all of this data into a model, only really a subset of this text will tell us whether it's sci-fi, fantasy, or romance. So here I've kind of bolded the components which I think would tell you whether it was fantasy, romance, or sci-fi. Whereas the rest of the text is kind of just context, it's for reading purposes. You need some context. You can't just have little bits of text within a book. So really you want your model to pay attention to particular components of this text and less so to other components. So one really simple way of going about this, actually it's not a simple way, there's many ways that you can achieve this, but it's by putting your instances all through the same network and coming out with scores or predictions for that network. So for example, if I was trying to determine whether an entire slide, an entire piece of tissue contained cancer or not, I would put patches through the entire model, and then I'd get a score for whether there was cancer or not for each patch. And then you kind of want to make a decision for each of those patches to make up the entire image itself. So it's an aggregation task where you've got lots of scores, which are shown here, and then you want to make an overall prediction based on lots of different scores. So here's the example that I was talking about earlier. So I have had an entire piece of tissue here, and I've taken lots of little different patches from this particular tile, pushed them all through a network, and the network has made some predictions as to which ones are healthy, which ones are cancerous. And not only that, it has a probability score attached to it as well, because I've used a softmax. And I want to aggregate all of these scores to combine into one prediction so that I can just say whether this image contains cancer or not. So there's many different ways that you can do that aggregation task. Some of the more simpler ways and also more commonly used ways are max pooling and mean pooling. And they're commonly used because they're very simple and straightforward, and they're very easy to implement as well. And it's just a very quick initial test that you can perform. And if it performs well using max or mean pooling, then that's your job done and you can move on. But however, there are some downsides, obviously. With max pooling, you're just taking the largest Y, so you're kind of ignoring a lot of the other instances. With mean pooling, you're not really, whilst you're taking account all of the instances, you're kind of ignoring the actual probability scores of each instance, especially if you have a wide variability of scores between all of those instances. So if you have a high one and a high score and a low score, you've kind of just averaged them out and lost that differentiation between the instances. So you can take it a little bit step further. You can use a linear softmax where you're weighting each score. So when you combine them, if you have a high score, you're taking into account that there was a high score there as well. You could take that another step further by taking the exponential of those individual probability scores. And then finally, you can take it even further by learning those weights. So how should you take into account all of those different instances should be learned. And that's actually what I'm going to talk about next. So this is a paper that I came across in my work. It's called Attention-Based Deep Multiple Instance Learning and came out in 2018. And they actually used an attention mill pooling technique and applied it to lots of patches, like I showed you earlier, in colon and breast cancer, as well as an MNIST bag data set as well, where they took MNIST and created bags from the MNIST data set in order just to show that it was working on a toy example. So I really like this paper because it gave you the toy examples as well as some real world data and how it worked in real world data as well. So this is how it works. You have a model architecture and you do push each instance through that model to give scores for each patch within your image or each instance within your bag, however way you want to define your problem. So this is the model here. So your images would go through here and would come out with a score. But in addition to that, you have this little network here, which is taken into it the outputs from intermediate layers within your model architecture and kind of learning a multi-layer perceptron here. And that would output another set of scores, but these are your attention weights. And then your attention weights would be multiplied by your scores, and that would come out with one score for all of your instances put together. So this multi-layer perceptron is essentially just a little mini network, and it kind of learns what instances should have a higher weight and which ones should have a lower weight automatically. It's a fully automated network. And the authors actually take this one step further and say that actually we can have gated attention here so that you can learn the relationships between instances as well. So for example, if I had tumor cells and they were surrounding lymphocytes, which are often associated with tumor cells, I can learn that that relationship is quite strong. Whereas if I had stroma around a tumor cell, that relationship might be weaker because stroma is found in other areas of the breast, not just around cancer cells. So learning the relationship between instances is another nice addition to this very simple architecture. And this kind of shows some of the results. They show some results in the paper, comparing it to max and mean as well. And you really see the boost in accuracy they achieve by actually learning those weights and rather not just aggregate information together. And that was the same for both the breast cancer and the colon cancer and the MNIST bag data set as well, which is really interesting and seems to work in practice as well. In fact, here they had particular gain in AUC values. The gated attention improved a little bit here, but less so here, which is quite interesting. So obviously it's task dependent and it's a little unclear as to whether it is worth implementing that additional gated attention or not. And so really, I think for me, the results weren't impressive enough to implement the gated attention, but the attention stuff is definitely worth looking into. So this will be our practical for Thursday when we're implementing a weekly supervised learning framework. We're going to build a custom model which takes multiple images. We may use the MNIST bag, but we'll figure that out with our TAs as well to have that a data set available to you. We'll push it through a network to come out with scores as you normally would do with a traditional classification approach. But then we'll build an attention network here on top of it and aggregate scores by combining them. And you may choose to use gated attention or just simple attention. That's up to you. But the backprop kind of happens as per normal. There's nothing new that needs to be added to the loss function term. So in practice, it's going to work like this. You're going to override your forward function in your PyTorch code. You'll create your custom layers here, and then your attention model will take the output from some of these layers, so FC1 and FC2, and output another set of weights which you can multiply by your output. So here I've shown you a diagram of our attention network taking in FC1 and FC2, which you may concatenate, and then learning a couple of layers, a couple of linear layers, and then simply outputting a 1 by n attention weights, where n is the number of instances that you have, or here we're actually going to create a batch which is representative of a bag. So you'll have multiple instances within a batch, and that makes your bag. And so we'll have 1 times n, where n is the batch size. And so we'll get into that in a little bit more detail on Thursday, but that was just to give you a quick preview about exactly what we were implementing on Thursday. So next I want to talk about some work that I worked on myself, based on the task that I showed you earlier, where I wanted to tell whether a particular piece of tissue contained cancer or not. And I arranged them into bags by taking patches within each slide and kind of grouping them together, where positive bags may or may not contain negative instances, and negative bags just contain healthy tissue and nothing else. So because we were working with deep learning neural networks, I found that when implementing this multiple instance learning framework, obviously we can't have the whole data set available in one go and learn the distances as we would do in the original implementation. You know, our data sets are too large. There's no way we could get it all into memory and kind of come up with summary statistics and measure distances between clusters. It's just not feasible. So instead, I came up with a technique whereby we would have many batches and come up with many statistics about each individual batch that gets pushed through my network. So I had 2 components to this. One was an autoencoder, which learned this kind of high dimensional space. So here I've projected it into a 2D space, but this is essentially a high dimensional space, and I use an autoencoder to do that. And then I clustered this space in order to create labels. And I called these cluster labels because they were estimated labels created from an embedded encoded space. So here is my autoencoder, or rather variational autoencoder, but you could use an autoencoder here as well. I push through an image through here, and the job is to reconstruct the original input and have our hidden embedding here. And once I've given it enough of these samples, which was very easy to do considering the size of my images, I can remove that second section and just use the first part as a way of gathering some low dimensional kind of signatures attached to each image. And then when it came to training a model that could recognize whether there was cancer in here, I would push a patch through this network and out would pop an encoding, which is being projected out onto this 2D space here. And I would repeat that for every image and every batch and so on and so forth until I came up with this kind of summary statistic of what the entire data set encompassed. So the way I use this variation autoencoder in the loss function is by simply adding an additional term. So usually you would have categorical cross entropy where you're comparing your labels with the outputs that come out the network. All I did was add an additional term which estimated the cluster label by clustering the high dimensional space and comparing that to a prediction which also came out the output. So these are the labels that come with the bag, but some of these might be correct, some of these might be incorrect. And also we have a label that we've estimated just purely based on features alone. And these also may be correct and may be incorrect because obviously we're just purely basing this on features alone and no human experts. So the idea here was by balancing both, they were complementary and could give more informative information to the model when it was updating its weights. So this was work that I presented in Europe in 2018 in the ML for Health workshop. And I also tested this on a public data set called Camelyon, where the task was to segment out tumor cells by just giving information about the entire image, so whether this contained cancer or whether it did not. And I created an inception net to do this and used my variation autoencoder setup to encode the space. So this was only a 24 length encoding, so a very small encoding space. And then use that in the inception net in order to come up with cluster class labels as well as the labels provided in the training set. So this is kind of one set of results which shows what happens when we do this. So ideally, we want to get this set up where we've identified the cancer within this image and we've ignored all the healthy tissue here. And our models did a fairly good job of ignoring the background and identifying cancer cells. It even captured this little pocket of healthy lumen tissue here, which was not captured in the segmentation that was done by an expert. And there's lower probabilities where the healthy regions are, but this can be much more improved. And my hunch is that here, my autoencoder, which was only 24 length, was not strong enough to distinguish between healthy epithelial cells and cancer cells here. So perhaps by making this bigger and perhaps by making this deeper so that it was capturing more complexities within our data sets, we could have improved this a little bit further as well. So this was kind of my initial step into multiple instance learning, and by reformulating this task into a series of patches and just giving course labels, but it seemed to work very, very well as an initial look into our data set. I will also mention that whilst it didn't perform exceptionally well in Camelyon, it performed exceptionally well in this bag data set. So the toy data set, it performed really, really well in that data set. It was just when we had subtleties between patches. So in the MNIST data set, the digits themselves are quite unique and there's quite a lot of difference between each individual digit. Whereas here, the patches were more subtle and there was less differences between patches. And that's really where our models tripped up, and therefore we needed a stronger representation to begin with. So that concludes the multiple instance learning component. And if you want to learn more about my work in particular, we can definitely do that. But I would like to give you some intuition into how multiple instance learning works by looking at attention at first, because this one gets into more complex models and there's less emphasis on learning the relationships between all of the different instances within each bag. So I'd rather we looked at really the relationship between all of these instances rather than boosting performance in very large data sets.